For the next session, I'm incredibly pleased to be welcoming on stage Mr. David Andre, who's the Chief Science Officer at X, the Moonshot Factory. David is a scientist, inventor, and entrepreneur who focuses particularly on AI and machine learning for time series and making decisions in times of uncertainty. David is also an entrepreneur who co-founded Cerebellum Capital, who used to be an asset management company powered by an AutoML system that discovered new kinds of trading strategies. So ladies and gentlemen, please welcome on stage David Andre.
Hello, everyone. I'm here today to talk about the impact of artificial intelligence. As the opening sequence to this conference illustrated, when many people hear that phrase, this is what they think of. They think of the dystopian future where humanity may be enslaved or possibly extinguished by artificially intelligent robots. Or perhaps they worry about programmers in a dark basement somewhere hacking up algorithms to exploit them. This is not the artificial intelligence that I think about, hope for, and work for every day. My kind of artificial intelligence looks a lot more like this. It's robots and sensors out in a field, gathering data from the real world to bring it into the virtual world so you can try to make something better. This is a proof of concept for a system to help agriculture become more sustainable. We brought this out in the field to test one simple thing, which is if you moved a camera through a field at high speed, could you still get pictures of the plants at a scale that they could be useful? That's why we did the prototype. When things get started, they're not terribly glamorous. I've been working in this field building janky prototypes like this to get that raw data into the field, into the computer rather, so you could figure out if you can do something useful with it. Let me show you where I got my start. This was in the late 1990s, and my colleague here volunteered to be part of a study in a sleep lab, and we attached nearly every sensor known to humankind at the time to him so we could tell what kinds of signals were coming off of the human body. Could we tell what sleep stage he was in? Turned out we could, and these kinds of prototypes were the precursors to the Oura Ring on your finger or the Fitbit on your wrist. There's a joke in computer science. Artificial intelligence is all the stuff we don't know how to do yet. As soon as we know how to do it, we stop calling it AI. We call it a product. We call it a tool. Many of you had to get here today, and maybe you use Google Maps. And when Google Maps very intelligently routed you around traffic, you didn't call that artificial intelligence. Many of you in this country may not speak Dutch. Maybe you had to communicate with someone who does. And maybe you use Translate. And you don't think of that as AI anymore. It's just a tool on your phone. Even when your car stays in the lane automatically, you think of that as smart lane assist, not artificial intelligence. I work at a company where we go out in the real world every day and get real world data and bring it in and try to do something useful with it to try to solve really hard problems by creating radical solutions. At X, Alphabet's Moonshot Factory, we choose our projects by thinking about problems so big that if they were solved, billions of people's lives would be better. We then get to do a fun part where we brainstorm science fiction sounding solutions to those problems. Many of them have no hope, they won't work, and that's okay, right? Because then we do the next thing, which is the super hard part of trying to find breakthrough technologies that can enable those radical solutions to solve the really big problems. Let me tell you about a few of our most famous moonshots. With Waymo, we taught cars to drive themselves. With Wing, we have drones that deliver packages autonomously at lower economic and environmental costs. And with Brain, we invented some of the core machine learning algorithms that today power the AI revolution. That was the past, though. Let me tell you about some of the projects we're working on today and some of the problems we're trying to solve. The world's population is going to grow by 1.7 billion people before 2050. Humanity has a problem. There's a lot of mouths to feed. We have to find a way to do that sustainably. Mineral is an agriculture project started at X who had the vision of figuring out how to supply the food with sufficient food without destroying our soil, our forests, or our waterways. They had the idea of what if we could see at the level of each individual plant and what it needed. But the problem is that measuring every individual plant today looks like this. It's someone out in a field with a ruler and a notebook writing things down. Mineral's key idea, their radical solution was, what if we could instead do this at scale with machine vision and artificial intelligence? So over the next few years, they did a really incredible thing. They went out in the world and worked with dozens of partners to try to gather this data. And as they did so, they built an incredibly valuable database of pictures of plants. Right? They were out there in the fields using those cameras I showed earlier to get those pictures. And with this database, they had something that's very akin to Street View, but for agriculture. Instead of seeing buildings, they're seeing what's happening with plants, and of course, the state of those plants and the condition of those plants. Here's a little video of this working in a wheat field. And the machine learning algorithms are capturing what's happening with every individual plant. They're capturing the status of it as well. When you see this, you can imagine combining it with data about the soil, about the genetic information of the plants, and with satellite imagery, and you start to get an idea of how you could have a much more nuanced approach to agriculture. One where we're no longer wasting 40% of fertilizer because it was misapplied. One where plants grow to their full genetic potential instead of 66% below it. Because in this future, we can apply farming techniques at the level of every individual plant. The key to Mineral's success is that the AI is only part of the solution. It's a tiny part. The important thing is the connective tissue all around it that connects it to the real world and the business realities of farming. This is why Mineral's worked with dozens of partners around the world, people like bean breeders in Colombia, Argentinian soybean farmers, and banana growers in the Philippines, because they knew that they needed to learn that the technologists didn't have all the answers. They knew their technologists need to learn the wisdom that had been accumulated in all these places and bring that into their models. Let me tell you about another problem we're trying to solve this way, and that's the climate crisis. We all know and have heard today how important this is. It's a looming danger for humanity. And this is why half of the projects at X are focused on this crisis. Some of them are involved in alternative energy production. Others are working on pulling the carbon out of the air and putting it into the soil and putting it into the ground. Another one of our projects in this space is Tapestry, our moonshot for the electric grid. The electric grid is the world's largest machine. It's been built over 100 years and kind of cobbled together over time because it had to be. Right? People had to repair a part of it, fix this piece over here, modify that piece over there. And because of this, the information about the grid is not held in any one central place. It's siloed. And so when there's a problem with the grid, the utility operators don't always know what went wrong or where that piece of equipment is. This is only becoming harder with billions of electric vehicles and solar panels coming online. The situation is so bad that in some places in the world, when a solar field is completed, it can take up to 10 years to get it onto the grid because of the bottleneck of utility companies being too scared and too conservative to move things onto their systems fast enough. Tapestry used a similar approach to Mineral to solve this problem. They went out there in the real world. They talked to people. They incorporated their information from the utility companies, such as the state utility operator in Michigan in the United States. They took their data, and then they went back out into the world and verified it by driving around using cameras. Then they integrated that information with other information that Google had, such as Google Street View and satellite imagery. They then brought all of that data into the computer to virtualize it and make a simulation. And once they had a simulation of the grid, they could do something incredibly interesting, which is to run multiple scenarios to help the grid operator understand what they could do safely and what they couldn't. Tapestry is using this today with grid operators around the world, including CEN, the national utility operator in Chile. They're helping them, because they can run simulations much faster, to achieve their ambitious goal to get fully off of coal and to be net zero by 2030. As we've seen with these two examples, we kind of have an approach here. We go out and get real-world data, we bring it into a computer, we use some smart algorithms and massive compute to try to make things better. There's one more problem that we're doing that we're solving this way, and that is the problem of the inefficient and wasteful supply chains that we now have in the world. There's this trend that we've noticed that companies don't seem to know where their own stuff is. And this is very true with supply chains, because you get raw materials somewhere, you manufacture a product somewhere, and then you give it to a carrier, and they're shipping it around the world, and you don't necessarily know where it is. The problem with this is when you don't have all the information, when something goes wrong, like a tanker turns sideways in the Suez Canal and blocks it, right? People don't know what to do because they don't have the necessary information. They can't manage what they can't measure. Chorus is our moonshot to address this problem. They have developed smart and cheap sensors that can go on every product to give every product a voice. Those sensors are then utilized with orchestration and management algorithms to do smarter things for the business. When we were starting this project, the pandemic happened, and the Chorus team came in contact with a group in New Zealand called Healthcare Logistics. Healthcare Logistics had the very challenging problem of delivering 11 million vaccines to all the people in New Zealand on time and under incredibly tight restrictions. All the vaccines had to be kept within 2 degrees and 8 degrees Celsius, right, or they would spoil. Additionally, the rules in New Zealand said that they had to be delivered from their manufacturer, where they were in cold storage, out to the clinics and hospitals within 12 hours. And this is in a country where it can take 24 hours to get from one corner to the other. The Chorus team was ready for this. We put one of the sensors in each and every one of the freezers that was being delivered from the central facility. That was in Auckland, and the little blue dots on the screen here are the shipments going out from Auckland to all the clinics and hospitals in the country. The graph below is tracking the temperature, and it's thankfully staying very nicely in the range that it needed to. Prior to Chorus's involvement, Healthcare Logistics would have had to put a sensor in the box, but it wasn't real time. It wasn't communicating in real time. It would have had to go back to their factory after it had been delivered, downloaded, analyzed, and only then would they know that some vaccine had been spoiled. And of course, that wasted time. That could potentially cost lives. So in the end, Chorus was able to help Healthcare Logistics deliver vaccines to 1,000 hospitals and clinics around New Zealand, enough for 2 shots for every citizen. This is the kind of real-world impact from artificial intelligence combined with data from the real world that I'm happy to work on and happy to share with you today. This is just one of the ways that Chorus's tech can help. Another one, briefly, is that we can use the same technology to track medical devices inside the hospital. Why is this important? Because 15 to 20% of medical procedures are postponed or delayed because the hospital staff can't find the necessary equipment. This, of course, can cost lives. And the reason they can do this on the Chorus team is they've developed smart algorithms to localize where the devices are inside the hospital, even though GPS doesn't work well inside. So for all of these projects I've talked about so far today, there's a common thread. We collect data from the real world, we touch that real world, we bring it inside, we do some simulation, and then we do some optimization. Mineral is optimizing agriculture for sustainability. Tapestry is optimizing the electric grid for decarbonization. Chorus is optimizing to minimize waste and cost in the supply chain. So another thing that we can do once we have the simulation for a particular problem is we can do something really interesting that was alluded to in an earlier talk, which is something called inverse design. Inverse design is where you flip the design problem on its head, and you ask the computer to do a lot more of the work for you. You tell it what you're looking for, you tell it what counts as good, and you tell it the rules it has to follow, the constraints on the solution, and then you get to use the power of massive compute to try to solve your problem. Right? This is super powerful because you often get things that you didn't expect. You get things that are weird by human eyes, but they might be incredibly clever solutions to the problem that a person would never have found. This field has existed for a long time. In fact, I've been working on it my whole career, over 30 years. But there's something really critical that just changed about this field, and that's the advent of large language models. Because it used to be that you had to pay engineers and programmers a lot of money and take a lot of time to program up a simulation for your domain. And you had to spend even more time every time something was wrong to fix the business constraints, right? All of that time meant that it was very difficult to get this kind of inverse design situation working for a given domain. But with large language models, you can go directly from intent, from what someone wants to do, to code, from a business constraint or business logic to code. And what this means is that we're entering a new era of computation, one that I like to call what you want is what you get. WowieWig, if you will. This new era of computation reminds me of the introduction of the printing press. Today's AI tools are bringing the power of massive computation and AI-generated content to millions of new people who are creating and improving their content and then distributing it. Just as the printing press expanded literacy beyond the clergy and the ruling class, today's AI tools are bringing the power of massive compute to millions and billions of more people. Before now, only programmers could really change the way computers behave. Previously, it required a programmer to meaningfully change anything. And if a regular person said to their program, hey, I don't like the way you're working, of course the program's not going to change, right? Have you ever tried that with your computers? Doesn't work. But in the future, instead of the inscrutable incantations given by today's wizard class, everyday people will be able to get their programs to change behaviors. And everyday people will be able to write the connective tissue and create the connective tissue that ties incredible problem solvers like optimizers, today's state-of-the-art optimizers, with the problems they know about best. We really want everyone to do this, not just technologists, because technologists are only part of the solution. We want everyone, from nurses to ocean biologists to folks working in forestry to factory workers, to be providing this connective tissue. Because we want the people who are touching a problem to be the ones able to solve the problem, because they understand the problem best. Let me tell you why I am so passionate about this accessibility of massive compute. I want to introduce you to my mom, Cheryl Andre. She taught me her love of computation, of computing, of mathematics, and how to debug just about anything. And she was an amazing woman who had a career as a programmer in a time frame when this was very difficult for a woman. She grew to manage her team, but sadly had to retire at too young of an age due to her medical condition. And she spent the last few years of her life, or the last few decades of her life, rather, in a wheelchair. But she never stopped fighting for accessibility. She fought for greater access for those in wheelchairs and those who are disabled. She fought for better access for those with her condition, so that doctors and medical clinics would share more information about her rare disease. She entirely was touching her problem. And I wonder, if she had had access to artificial intelligence, what would she have done with it? What would she have done with AI? As I think about the future, I am full of hope and joy that the promise of artificial intelligence has finally come to fruition as a tool to help humanity tackle some of the biggest problems we share as a species. We are at the beginning of this journey, and this can be a wonderful time where all of us can work with experts in the fields that we're interested in to create the connective tissue that can allow massive compute to actually make a difference on these problems. At X, I work on this every day. What if we could create solar panels that were 3 times more efficient than the ones we have today? What if every human could have access to a large language model and an AI system that could help them with their education or their mental health? What if we could use these tools to design plants to improve our nutrition, or medicines to improve our healthcare? Many people think that it is someone else's problem to solve these hard problems of the future. Businesses think that governments or nonprofits should do it. Governments and nonprofits say they don't have the resources. Universities and academic institutions say that they don't have the means to turn these things into reality. And I ask you, I think it's all of our problems to do this. all of us can get out there, get out of our safe zone, take a risk, and start a moonshot. And so I leave you today with one question. What will you do with AI? Thank you.